Kirkle Math. All right, ladies and gentlemen, here we are with 7.3, where we're learning how to multiply special cases. So you're in your student companion on page 146 and 147. Now, what does this mean by special cases? Well, it basically means that there's a couple different things that when we multiply them, we can easily know the answer because of patterns that we've seen when multiplying them. So we don't have to multiply them all the way out. Could you still multiply them all the way out? Yes. But in these special cases, you can actually quickly get to a solution by memorizing some of these kind of special things going on and these little tips and tricks. Sorry. Okay, so the first one is what happens when I square a binomial? So why would a plus b squared be a special case? So here we have a couple different ways we're going to show you. So here's using the distributive property, and I could still, like, you could totally still do like a plus b times a plus b, and then go your first and your outside and your inside and your last. You can still do that. This is not taking that away, but like I said, this is kind of those special things that we found some patterns that we can actually change. So over here, you'll look that they rewrote it, a plus b times a plus b. Using distributive property, we're going to distribute the a to both and distribute the b to both. And what we end up getting is a squared plus ab plus ba. And remember that a times b is the same as b times a. They're just rearranged. It's the same reason why 3 times 4 is the same as 4 times 3. It's the commutative property of multiplication. So they rearranged the a and the b so that they got 2 ab's, and then you had b squared. So when you multiply, when you have something squared, you're basically going to always get, and that's where, oopsie. Here we go. Doop. You're going to get this right here. You're always going to have the first term squared, then the second is going to be twice the first and last terms multiplied, and then you'll get the last term squared. And we'll do some examples so that you can see how that works. Okay, a visual model on how it works here is if I made that table and I multiplied them out, I would have a squared, ab, and b squared. So I don't even have to do the multiplication. I can kind of know by looking at this that I'm going to have this one squared, and the combination of the two being multiplied times 2. So here's a good example of that. So we have 5x minus 3 squared. So this is our binomial being squared. So using the pattern that we saw in part A, I'm just going to rewrite everything here with my first term squared, my last term squared, and the product of the first and last terms in the middle. So you can see here they did 5x squared, then they did negative 3 squared, and then they multiplied the two terms and times by 2. And in the end, they got 25x squared minus 30x plus 9. So again, you can see first term squared, last term squared, two terms multiplied together times 2. All right, in this next one, we are looking at how can I now use this information to help me? So if I have 29 squared, how can I use the square of a binomial to help me figure out the answer to this? So basically, they just rewrote the product as a difference of two values. So they basically rewrote 29 as 30 minus 1, and they squared that. Then they used the pattern to do 30 squared minus 1 squared, and then 30 times minus 1 times 2. So you're going to get 900 times 900 on the beginning. At the end is just 1, and in the middle, 2 times 30 times negative 1 is negative 60. Put them all together, and you have 841. So in general, you can use the square of a binomial to find the square of a large number by rewriting it as a binomial, as a sum or a difference. Okay, so just a way to use it. All right, so here, go ahead and try that. Go ahead and use the pattern that we have over here to do this binomial squared, and then use the information about finding the square of a large number, rewrite it as a binomial, square that, and see if using the pattern can help you find the answer. All right, our next special case has to do with finding the product of a sum and a difference. So when I have a plus b times a minus b, again, I can just distribute this out. I can do a times a plus a minus b plus b times a plus b times minus b, and I can combine like terms like we're used to, but a faster way to do that, once you distribute, you'll notice a pattern. And that pattern is that these two middle values, okay, these ones that normally we would have had two of these products, because they're opposite signs, they end up dropping out. So those two parts in the middle, excuse me, go away, and I'm left with just the first term squared and the last term squared. So the products of two binomials that are opposites, a sum and a difference, results in the difference of two squares. So if you want to add this to your notes here, I kind of laid that out as well. It's the same thing over here, just a little bit differently. But basically, we're going to do a times a, which is a squared. Here's the two that cancel out, b times b, which is b squared. And because this is negative, it's going to be a difference of two squares. So let's go ahead and try that out. We're going to use 5x plus 7 and 5x minus 7. And we're going to use our quick little cheat right here. So instead of multiplying them out, I'm going to say that this is 5x squared, and this is going to be minus 7 squared. And I'm going to get 25x squared minus 49. So let's see over here. Here we go. Using our pattern, we got the same answer here. There you go. And again, we're now going to use this new tool that we have to apply it to something that we might use in the real world. So how could we use the difference of two squares to find the product of 43 and 37? Well, just like the last one, you probably guessed it, we're going to rewrite our numbers as a product of a sum and a difference, right? So 43 is 40 plus 3, and 37 is 40 minus 3. So if we rewrite them as such, then all I have to do is square the first term and square the second term and set them as differences, and I can find the answer really quickly instead of actually multiplying them out. It's kind of a way to mentally find the answers to large numbers. You can do this one in your head instead of having to do, traditional way. All right, so give it a try. Using our method here, knowing this is the difference of two squares, solve A, and then using this, write to a sum and a difference that are the same, using the same numbers, and see if you can find the answer to 56 times 44. All right, we're going back to the square of a binomial, and we're using this in a word problem this time. So we're actually going to, again, use this tool that we found to apply and solve a problem. So a graphic designer is developing images for icons. The square pixelated image is placed inside a border that is 2 pixels wide on all sides. If the area of the border of the image is 176 square pixels, what is the area of the image? So we're going to let x represent the length and the width of the image. So x is the length and the width of the actual image. So you can see that this is the white part, okay? And because it is a square, the length and width are the same. We're then going to calculate the width with the border. So knowing that the red part is 2 on both sides, that's going to add 4 total in our frame for our height and width. So we're going to take the picture height plus the extra border, and that's where you get here. Okay, then we're going to find the area, and because the area of a square, so down here the area of square is side squared equals the area of a square. They just took the x square or x plus 4 and they squared it, just like a square of a binomial like we did before. So before I even hit compute, we're going to try to figure it out with our pattern here. So we're going to take the first term and square it. So that's going to be, I'm going to use orange down here, that's going to be x squared. We're going to take the last term and square it. That will be 4 squared. And then we're going to have 2 of x times 4. So that's going to end up with x squared plus 8x plus 16. Let's see if we're right. Here we go. So they went ahead and applied the property as well. Oh, I forgot. This part is right. X squared plus 8x plus 16. But then you'll notice here that because we want just the border, we have to get rid of the image area. So they're subtracting x squared, which is going to get rid of this. And we're going to be left with just 8x plus 16. Because we know what the area is of the border, we know the border area is 176. They set that equal to it, and they solved and got 20. So x, which is the image length, is a 20 by 20 image. So here's your turn. A graphic designer is developing on alternate icons. The square pixelated image is placed inside a border that is 4 pixels wide on all sides. If the area of the border of the image is 704 square pixels, what is the area of the image? So it's the same type of idea. You have a different area of the border. And if we go back here, because this is 2 pixels wide, I feel like this image is wrong. This should actually say 8, because it's telling us that the square pixelated is inside a border that is 4 wide on all sides. Yeah, see if you can solve with the information that's given. All right, so on this page you have some more notes. You probably already have most of these, but in case you missed anything, these are our 2 special cases: squaring a binomial and multiplying the product of a sum and a difference. So they explain them in words, what goes on here, okay? And then down here they give you the algebraic example. So if I am adding, here's what it looks like. If I have, if I'm squaring a binomial that is using subtraction, then I would actually have the same problem, except instead of adding the twice the first and the last term, I'm going to be subtracting. Okay. Over here they have another example, and then they have an example with numbers, not just the general letters. And that's all I have for you. It's pretty straightforward, not too bad. Go ahead and try finishing those got it problems, and then we'll practice some more in class.